Hey students, got a question here from, looks like our optics, chapter 25, number 58. As you guys are getting ready for the exam, let's read it here together. It says here, a shopper that is standing 3 meters from a convex security mirror sees his image with a magnification of 1/4. Okay, and so I guess it would look like this a little bit, and we would have an image. And one thing we learned about this convex mirror is it made things appear inside virtual upright and smaller. That's all this mirror ever did. That's why I kind of refer to it as the boring mirror. Unlike the concave mirror, where you could have things either bigger or smaller, and then bigger right side up or bigger upside down. So there are 3 combinations. And then this is the fourth option. And I guess the flat mirror would be the 5th option, where it was same size and kind of a special case between the two. Anyways, this is this idea here. And then it says, where is this image here? So I guess the first thing I need to do is to say, all right, we have the magnification, call it M, which is minus the height of the image over the height of the object. And so they say the magnification is 1/4. And so this would tell me that 0.25 times the object distance, so that would be this right here, equals then negative of the image distance. So that's the first piece of information. And the second one is 1 over object distance plus 1 over image distance is 1 over focal length. Where for mirrors, not lenses, but for mirrors, the focal length is the radius over 2. Of course, then the other hard part about our optics is keeping track of those plus or minus rules. And I know you've had a couple of people asking me on Zoom, as well as I sent out that video. It is a little bit of a pain, I would admit. It doesn't kind of fit what we like to do normally in physics, and that is just have a few simple principles that explain a universal phenomenon. But these rules that if we commit ourselves to memorizing them are great because they allow us to use this same equation right here, and this equation, these 2 equations will now work for the concave and the convex mirror, as well as the concave and the convex lens. And so, yes, memorizing these rules of plus and minus are a pain, but on the other hand, they are totally worth it, because then we can use the same equation for all of our mirrors and all of our lenses. And that's, like I said, totally worth it. So in this case, we're going to have to learn the plus and minus, or remember what the plus and minus is for the radius of curvature. And this is the negative side. I like to say, you know, the radius of curvature is probably in my picture kind of like over here somewhere. So if I had a compass and was sweeping it out, it would be where, you know, the light never gets to, because the light hits here and bounces off. And my definition, or my way of kind of remembering it, is a little different than the way the author describes it. But I like to say, if this radius of curvature is where the light never gets to, then it's negative. If it's where the light actually gets to, so if it was curved the other way, concave, and the radius of curvature was right here, and so the light comes in, you know, and goes by it, then I would give it a positive. And I like that description because that works also for image distance. So as this light comes in and bounces off the mirror, it never gets to the image that is formed. So this image distance should come out to be a negative number, as well as the focal length and radius should be a negative number for this case. And we need that right here when we do something like this. 1 over object distance plus 1 over image is then equal to a shopper standing 3 meters. Oh, my bad. I like what I said, but I was thinking they gave us the radius of curvature. So now I'm glad I'm reading it here a little more careful. All right, let me try this again then. So the shopper is standing 3 meters. So even though this is all true, I should have right here just said, okay, this is 0.25, and the shopper, the object distance is 3. And so this is 3/4 or 0.75, and that is negative of the image distance, or put another way, the image distance is a negative 0.75 meters. Okay, so that is, as I was saying here, a negative number, and sure enough, that's our virtual image. So we have both the object distance at 3 meters and an image distance then at a negative 0.75. Okay. Which is really what I should have done right away. Like I said, I was thinking this 3 was the focal length or radius or something, and it's not. It makes it a much easier problem because that's the answer to A, where is the image? And so the image here is 0.75, and the negative means it's behind the mirror. It's where the light doesn't go. Sometimes we call that the virtual side of the mirror. We never like to call it left or right of the mirror, but most of the time when we draw our mirrors, we draw light coming from left to right like we're reading. But of course, you could always set the mirror the other way and the object is over here. And so calling it left and right is not a good idea. And then sometimes our mirrors are up and down, so then we got top, bottom. So we never like to say left or right or top and bottom, but we will say behind the mirror, or we will say the virtual side of the mirror, or we will say where the light never goes, which obviously is behind the mirror. Now, part B, when it says, what is this focal length, as I was beginning to say when I was misdirected, that this focal length should come out to be a negative number because it's over here where the light never goes. So let's see what the math gives us. So this would be 1 over 3 plus 1 over negative 0.75 is equal to 1 over the focal length. And those of you who've watched other videos know I like to write it this way: 3 inverted plus a negative 0.75 inverted is then equal to the focal length inverted. And then that way, if I go 3 inverted added to a negative 0.75 inverted, and then take that whole quantity and invert it, I get the focal length. And it makes it really easy to put that into the calculator using the reciprocal key right here. So I could go 3 reciprocal, and then, I don't know if you want to say plus a negative number or just go minus. I'll go minus 0.75 reciprocal. Then I like to hit enter and then just take the reciprocal of that, which wasn't really necessary with the calculator, but gives me a focal length of -1. And for that matter, would technically give me a radius of then -2, which might be the next question. Yeah, so B, what is the focal length? So -1. And then what is the radius of curvature? -2. Now, I must admit that some people like to put radius in its absolute value and put a +2. So if you put a +2, that wouldn't be unreasonable. I don't really like it here. I think it's better to say a -2 because this implies that we're talking about this shape instead of this shape, so a convex instead of a concave. And we already know it's convex. They made it very clear, so we don't really need a plus or a minus in this problem. So the absolute value would be fine. And like I said, some people don't like calling distances with a negative, but here I think it can serve a good purpose. It can serve the purpose of telling me that the distance is actually 2 meters, and the negative tells me which side of the light and the object and the image, and I can put all those together because the negatives have an important piece. All right, well, anyways, I don't think there's a D, so yeah, and so good. We'll call that done, and hopefully that helps someone. And then I'll go on to the next question I have, and you can see it already printed. I'll make a 59 here in a second.